Hello there, Mr. Sutton here, bringing you the AB Calculus 4-2 homework solutions on increasing and decreasing intervals. For this problem, we're trying to figure out which interval this function is increasing on. So to do that, we need to figure out the first derivative. That's going to be 300 minus 3x squared. And then we need to find some critical values. So let's start by setting this equal to 0. And now solving this, we can take out a 3 here. So that's going to be 100 minus x squared inside. And then with the stuff inside, I can just add x squared to the other side and square root. So this is going to equal 0 at x equals plus or minus 10. So let's go ahead and graph that out on a number line now. So here's my f prime line. I've got negative 10, positive 10, and now let me try some values in each interval. If I try something less than negative 10, like negative 11, well, this would be 100 minus something bigger than it because we're squaring a negative. So that's going to come out negative inside there, giving us a negative result. Something between these numbers, let's try 0. 100 minus 0 is going to come out positive. And then something bigger than 10, like, well, positive 11. We get the same result as when we plugged in negative 11 because we're squaring. So this is 100 minus 121, comes out negative. And we just have to look now for increasing. We just need to look at the positive intervals. So our function is going to be increasing on the interval from negative 10 to positive 10. And then that's going to be answer choice B. Now, if you're worried about these brackets, we can include negative and positive 10 in the interval or exclude it depending on your philosophy. They included it, so we're going with that answer. Choice B. For this problem, we want to know at what x values this function here is increasing. So to figure that out, I need to look at what the first derivative is doing and do some sign analysis. F prime, this is going to require a product rule. We've got two functions being multiplied together. So let me bust out the box and ribbon here. I've got x squared minus 3 as one of my factors, and e to the negative x as the other one. And their derivatives now, this polynomial is just going to become a 2x using the power rule. And for this e function, this is going to be e to the negative x times the derivative of the inner function, which is negative 1. So then negative e to the negative x. Multiplying this out with the ribbon now, I've got 2x e to the negative x. And then I'm going to just go ahead and immediately distribute this negative e to the negative x to both of these terms. So that gives me a negative x squared e to the negative x. And then this is going to be a positive 3e to the negative x. And then I want to figure out when this thing equals 0 or undefined. But I don't think this is going to be undefined anywhere since e is an exponential function. That's always continuous. And a polynomial, the x squared, is also going to be continuous everywhere. So what I can do to solve this is factor out an e to the negative x. I've got a common factor of that. I can't combine any terms yet, but let's see what happens if I factor that out. So, and also, because I've got this negative x squared in here, I'd like that to be positive because I'm just kind of thinking ahead here. There's probably going to be some quadratic I need to factor. So let me take out a negative e to the negative x, and hopefully the stuff that's left inside will be a little bit nicer to deal with. So if I do that, and I'm just going to write these in decreasing order of exponents now, this middle term here becomes a positive x squared. And then just going down the pecking order for degrees, this next term, 2x, this is going to become a negative 2x. And then finally, this 3e to the negative x, this is going to become a minus 3. So I changed the order a little bit just because I knew I was going to be factoring this down the road. All right, well, the stuff inside here, we're going to have to figure that out in a minute. But right away, I'm just going to discard this negative e to the negative x. Since this is an exponential function, we know that it can't equal 0 anywhere, so it's not going to give us any critical values. So factoring this next one now, things that multiply to negative 3 and add up to negative 2, that's going to be positive 1 and negative 3, so x plus 1, x minus 3, which means we have critical values at x equals negative 1 and positive 3. Let's go ahead and put those on a number line now, do a little sign analysis, and see where this thing's increasing. So here's my f prime number line, and I've got critical values again at negative 1 and 3. Testing out some values in each interval. Let me test out negative 2. Seems like a good one for this left interval. Now, when I'm doing this, we have to take this negative e to the negative x into account. But this is always going to be a negative term. E to the negative x by itself, since it's exponential, always stays above the x-axis and is positive, but we've got a negative multiplier out in front of it. So we're always going to have a negative no matter what we plug in, kind of being waiting to be applied. And let's also look at these factors now. If I plug in -2, this becomes a negative. This is another negative. So we have 1, 2, 3 negatives. Odd number of negatives gives us a negative. And now between -1 and 3, I'm going to test out 0. Again, we automatically get a negative out of this negative e to the negative x. And then I've got a positive and a negative. 2 negatives gives me a positive. And then finally, bigger than 3, let's try 4. We have the negative out in front and positive, positive. So that's a negative overall result. We wanted to know where our function was increasing. So we can say then that f is increasing wherever f prime is positive, so between -1 and +3, which gives us answer choice D. For this problem, we're given an f function whose derivative is f prime equals x squared minus 2 over x. So this is the first place we have to be careful. They're giving us the algebraic form of f prime, not the original function. So on which of the following intervals is f decreasing? Well, if I want to know where f is decreasing, that means I need to know where f prime is negative. So we're going to find critical values for f prime and then do some sign analysis. I'm going to start by converting this into one big fraction, because that makes it a lot easier to figure out places where it's 0, undefined, all that stuff. So to do that, I need a common denominator. The only denominator is x here, so I'm going to turn this x squared into something over x. To do that, I multiply by x over x, so that's actually going to be x cubed over x. And then if I combine it with this fraction, I'm going to have x cubed minus 2 all over my common denominator of x. So just algebra fraction math kind of going on there. And now I need to know where this thing equals 0 and is undefined. Let's talk about the equals 0 part first. So if we have x cubed minus 2 equals 0, because we need to zero out the numerator to make the whole fraction 0, if I add 2 and then cube root both sides, I have the cube root of 2 as the value that makes this thing 0. Now, I don't know what decimal that is, and I don't need to know because it looks like I have that in some of the answer choices. This was a no calculator problem anyway. Now, the only other thing I have to be careful about is this derivative is undefined, does not exist at x equals 0, because 0, if you plug that in, is going to zero out your denominator. So f prime is dne at x equals 0. So this gives us two critical values to do some sign analysis around. So here's my f prime number line, and I'm just going to use the fraction version of this to do my sign analysis to make it a little bit easier. So I've got critical values at 0 was the first one, and then a third root, cube root of 2. Something less than 0 I can test out. Let me try out -1. If I try that in my fraction, this is a negative minus 2, so that's a negative numerator. Negative denominator gives us a positive overall. Something between 0 and cube root of 2. Well, if you don't know your cube roots very well, this can be a little bit tricky, but the cube root of 2, at the very least, we know that's bigger than the cube root of 1. And the cube root of 1 is just 1. So 1 is actually between 0 and cube root of 2. And if we plug that in, we have a negative numerator, positive denominator, so negative overall. And bigger than cube root of 2, there's lots of things we could pick. I went with 2, but you could have gone with 1,000,000 if you wanted to. And that gives us a positive numerator and denominator for positive overall. So taking a look at this, if I want to know the intervals where f is decreasing, again, I needed to know where f prime was negative. And we've shown here that it's negative between 0 and cube root of 2. So then f is decreasing on the interval from 0 to cube root of 2, which is going to give us answer choice D. Now, if you're wondering about the parentheses versus the brackets, we can include the root 2 because the function is actually defined at root 2, and you're always allowed to include the border values when you're doing these intervals of increasing, decreasing, as long as the value is defined on the original function. 0, however, makes the original function, well, it makes the derivative undefined. It probably makes the original undefined as well. So that's why they left it out and excluded it. It can't be a decreasing interval if the function doesn't exist there to begin with. For this problem, we have a table giving values of a continuous function f at some values of x. We're told that f has exactly 2 critical points on the interval from 10 to 14, the open interval, We want to know which of these is true. So this is one of those process of elimination kind of deals. Let's take a look at all of them now. And now just one thing to observe on this table as we look at our values. So we've got a value of 5 for the function, then we go down to 2, back up to 3, we go all the way to 6, and then back down to 5. So they're telling us there's exactly 2 critical points. So we know that there's 2 turnarounds that are happening on this and no more. So moving on now. First option, f of x is greater than 0 for all x in the interval from 10 to 14. Well, all the f of x values they showed us are positive, but are we guaranteed that this function always stays positive? For example, when we go down from 5 down to 2, how do we know that we didn't go even further below, like to -1 and then back up to 2? Or how do we know that we didn't go down below after we hit 2 and before we went up to 3? So we could go negative on the interval somewhere between 10 to 12. We don't know exactly when this function turns around, only that it does turn around somewhere between 10 and 12, x equals 10 and 12. So A is a no. We can't prove that we stay positive the whole time. Now for this next one, f prime exists for all the x in the interval from 10 to 14. Certainly we are continuous, so that's a condition of f prime existing, of differentiability. However, are we guaranteed that the limit actually, the left and the right limit matches up for the derivative everywhere on this interval? We don't have a guarantee. One way you could be continuous and still have these turnarounds here and have f prime not exist, you could have a corner or a cusp somewhere in here. That would allow you to turn around while violating this f prime existing piece. So that's also a no. Can't prove that one either. Next one, f prime less than 0, negative for all x in the interval from 10 to 11. So basically we're saying that we're decreasing the whole time between x equals 10 and x equals 11. Certainly, on average, we had to decrease to get from 5 down to 2. But again, just like with the first answer choice, how do we know we didn't go below 2 and then back up? And then, we could have a turnaround happening before y equals 2. So 2 could be on the way up, on the way to 3. So because we can't prove that we didn't turn around before we got to y equals 2, choice C also cannot be proven. And that leaves us with one more. D is looking pretty good because it's the only one that we haven't disproven yet. But let's see if we can actually prove this one. So f prime of 12 not equal to 0. So they're saying that basically that there's no critical value at x equals 12. Can we prove this? We can. We know that because we're going down and then back up between 10 and 12, there's a critical value somewhere on the interval from 10 to 12. We also know that since we're going up to 6 and back down to 5, there must be a critical value to let us turn around somewhere in the interval between 12 and 14. They also told us there were exactly 2 critical values, and this is the key here. If you have exactly 2 critical values, I'm not sure what I just did there. There we go. Since you have exactly 2 critical values, that means that you cannot have a third critical value at exactly x equals 12. You've already used up your critical values. So what this means is that then if there's no critical value at x equals 12, then f prime of 12 can't equal 0. It also can't be undefined because that would also give you a critical value. So that means that D is true, so that's the one we're going to pick. On this problem, we're given this f function, kx over x squared plus 1, where k is a constant. We want to know what k values make f strictly decreasing on the interval from -1 to 1. So if I'm talking about increasing or decreasing, I need to know a little bit about f prime, the derivative of this f function. Specifically where f prime is positive or negative. So I'm going to start by taking a derivative and seeing what happens. For that, I'm going to need the quotient rule on this. So let me set up the box and ribbon. So I have a numerator of kx, denominator of x squared plus 1. Now their derivatives, k again is a constant, so the derivative of kx is just k. Derivative of x squared plus 1 is 2x. Using the ribbon to multiply that, I've got k times x squared plus 1, and then minus kx times 2x. So this is u prime v minus uv prime. And then v squared down here, that's going to be x squared plus 1, the whole thing squared. I need to clean this up a little bit to figure out where this thing is positive or negative. So let me distribute the k here. That's kx squared plus k. And then this is going to be minus, let's see, 2kx squared. I can clean it up a little bit more. Specifically, I notice I have a common term here, kx squared and negative 2kx squared. That's going to be minus 1kx squared if I combine those. So I can write k minus kx squared then for the numerator. Okay, now that we did all that algebra, we want to figure out where this derivative is negative, is less than 0. Now, this might seem a little bit tricky because we have two unknowns. We have x, of course, and then k. I mean, it's constant, but we don't know what constant it is. And here's all our options. It turns out, though, they've actually given us enough information to figure out what k has to be to make this whole thing negative. So if I'm doing sign analysis on a fraction, I always have to look at the sign of the numerator versus the sign of the denominator. Let's deal with the denominator first. The denominator, no matter what you plug in for x, you're going to be squaring it, which is going to make it positive. Then you're going to be adding 1 to it, which is going to make it more positive. Then you're going to be squaring it again, which if there was any lack of positivity, you can't avoid being positive after everything that's going on down here. Really, this 2 outside here would have done it. So x squared plus 1, the denominator, we know for a fact is positive, is greater than 0. What that means is for this whole fraction to come out negative, it must be the numerator, k minus kx squared, that comes out less than 0. Well, what values of k will make the numerator less than 0? To figure that out, it would be a lot easier if we were in a situation where we had multiplication instead of subtraction, so we could use more sign analysis. Well, if you look at these two terms, they both have a k in them, so I'm going to factor a k out of this. That's going to be a k on the outside and a 1 minus x squared on the inside. And now if I look at this, in order to be negative, one of these things has to come out negative. We don't know what k is. That's kind of what we're trying to figure out. So let's look a little more closely at this 1 minus x squared factor. What is 1 minus x squared going to be? Well, we would need to know what x is in order to tell you that. Now, they did tell us in the problem we are on the interval negative 1 to 1. They didn't ask about k values anywhere else, just if x is between negative 1 and 1. If x is between negative 1 and 1, that means that you're going to be squaring something that's between negative 1 and 1, which is going to make it a number less than 1. Like if you square 0.5, it becomes a number less than 1. So you're basically doing 1 minus something less than 1 here. 1 minus something less than 1 has to come out positive, which means that for this whole thing to come out negative, it must be the k value that was negative this whole time. So based on that, we can conclude k has to be less than 0. That will make this a strictly decreasing function, and that is answer choice A. On this problem, we are given the first derivative of a function, this f prime function over here, sine of x cubed minus x. So that's some sort of weird polynomial inside a trig function hybrid, and that's on the interval 0 to 2. We want to know on what interval in this 0 to 2 interval f is increasing. So basic idea is if f is increasing, f prime is positive. So we just need to figure out where f prime is positive between 0 and 2. We can figure that out by just graphing this on our calculator. This is a Desmos graphing problem. So let's figure out where f prime equals 0, our critical values, and then we'll sort of build our analysis around that. So go into Desmos. Let me just call this the g function here. G, f prime, same kind of idea. So that's going to be sine of x cubed minus x. And here's what that crazy function looks like. Now, we only care about the interval from 0 to 2. So let me go ahead and just change my settings here. My x-axis, I'm going to make that go from negative, I'll make it a little bit less than 0, negative 0.2. And then I'll make that go to 2.3, a little bit more than 2. And here is what my graph looks like. So critical values between 0 and 2. We don't need to worry about 0 itself, but we have a critical value at exactly 1, and also another one here at 1.691. And there's another one just a little bit past 2 that we're not going to worry about because it's outside of our interval. So here's the graph that I just found on Desmos. Blew it up a little bit here. And then, again, 1 and 1.691 are the two critical values out of that. Now, just doing a little sign analysis, we see that f prime is below the x-axis, so negative between 0 and 1. It's positive above the x-axis between 1 and 1.691, and between 1.691 and 2, we're negative again below the x-axis. Since f prime is positive between 1 and 1.691, that means that f is going to be increasing on that interval. So that's going to match up with choice B. On this no calculator free response problem, we have this figure here with the graph of some function which models the height of a skateboard ramp, and this function meets these requirements. So at time 0, the value of the function is 0, and so is the slope, which looks about right. At x equals 4, somewhere over here, the value of the function is 1 and the slope is 1. Interesting. And then between 0 and 4, the function is increasing. Well, this graph certainly looks like all of that could be true. So now our first part here, let f of x equal ax squared. Okay, let it be so. A is some non-zero constant. They just want us to show it's not possible to find an a value so that f meets this requirement here. All right, well, let's start by assuming that this does meet requirement 2, and then seeing what happens if we take that to its logical conclusion. So let's say that it meets the first part of this where they said at x equals 4, the value of the function is 1. That means f of 4 has to come out to 1. Let's make that happen. So if we do f of 4, we're basically doing a times 4 squared, and they're saying that has to have a value of 1. So let's set that equal to 1. Well, for this to be true, that means that a has to have a value of 1 over 4 squared, or 1 over 16. There's no other a value this could possibly be to meet this part of condition 2. So if this a value can be shown to not work with the other part of this condition, then we've proven that it's not possible to find an a value that works. All right, well, let's go ahead and now that we know what a has to be, let's plug it into our original function. So we can now refer to f of x as 1 over 16 x squared. Now, the second part of our condition, they said the slope of the graph is 1. That means f prime of 4 has to have a value of 1. Let's find f prime in general. That's going to be, using our power rule, that's going to be 2 over 16, or 1/8 x. Let's go ahead now and see what happens if we do f prime of 4. Well, that's going to be 1/8 times 4, which is going to be 4 over 8, or 2. Now, they gave us a value here of 1. They said the slope had to be 1. 2 does not equal 1. Therefore, we've shown, since there's no other a values we could have used, that that a value does not exist. For this problem part, they're giving us another function, g of x, which equals cx cubed minus x squared over 16. They want a c value so that this function meets requirement 2, where the f function failed in part A. Well, let's start by figuring out what c value would make this first part of the rule come out true. So we need g of 4 to equal 1. Well, let's start by just plugging 4 into the g function. So c times 4 cubed minus 4 squared over 16. To make my life a little bit easier before I set this equal to 1, let me simplify this. So this is going to be 64c minus, this is really 16 over 16, so minus 1. And again, that has to have a value of 1, they said. So with this equation, I can solve for c. If I add 1 to get 2 and then divide by 64, I can write c equals 2 over 64, or 1 over 32 if we simplify it. Now we found our c value, but we haven't actually proven that it meets the whole condition. All that we've shown is that it gives us the function value, but not the slope. So just like before with part A, we have to go ahead and figure out g prime, and then see what happens if we plug 4 into that. Before I do that, let me rewrite the g function with 1 over 32 plugged in. So I can write this as 1 over 32 x cubed minus, we'll say 1 over 16 x squared, just to make it a little easier to use my power rule. And now let me find g prime for this. That's going to be 3 over 32 x squared minus 2 over 16, or 1/8 x. Let's go ahead and actually plug 4 into this now and see if we end up getting a slope of 1 like we're supposed to. So we've got 3 over 32 times 4 squared minus 1/8 times 4. Well, 4 squared is 16. That reduces with the 32 down here to give us a 2 in the denominator. So this first term then is just going to be 3 over 2. For this one, we've got 4 over 8, which is 1/2, so we're subtracting 1/2 from 3/2. That's going to give us 2 halves, which we know is 1. That is the slope that we were supposed to get, so we've shown that we got our c value here. For this problem part, using our g function and c, the value of c from part b, they want us to show that g does not meet this requirement, third requirement, which says that between 0 and 4, the x value 0 and 4, our function is increasing. Now, by this, they mean it's increasing everywhere between 0 to 4. If they just said increasing, they mean increasing for all x values along this interval. So to disprove this, we just have to find a single x value between 0 and 4 where the function is not increasing. To figure out where the function is increasing versus decreasing, we need to talk about g prime. So I'm just going to rewrite g prime from part b. Here was the g prime that we came up with earlier in my work, 3 over 32x squared minus 1/8 x. So we just need to plug an x value into this that makes it come out negative. If we want to show the function's not increasing, we need to show it's decreasing. All right, well, we could just start plugging in numbers between 0 and 4, but I mean, who knows how small this window of non-increasing actually is? Some of the numbers might actually come out positive if we plug them in. So to make our lives a little bit easier, I'm going to set this equal to 0 and find some critical values. And then we can narrow it down and figure out exactly what intervals we should try out. So to make that part of this easier, I'm going to actually factor out something. I'm going to take out an x from both of these, and I can also take out a 1 over 32, which seems kind of crazy, but we're going to make this work. So if I take 1 out of 32 out of 3 over 32, that leaves me with a 3, and we also still have an x left over in there, so 3x. And this 1/8, you could think of this as 4 over 32. If I factor out a 1 over 32 from that, that leaves me with just minus 4. So that gives me critical values at 0. And let's see, if we add 4 and divide by 3, 4/3. So basically, we have to test out a number between 0 and 4/3. And then there's a possible sign change in g prime at 4/3. So if we don't get what we want on this first interval, we'll try something between 4/3 and 4. And if that doesn't work, we're kind of out of luck. So a number between 0 and 4/3, an easy number, would be 1. So let's do g prime of 1 and see what happens. That gives us 3 over 32 minus 1/8. 1 is a very nice number to plug in here. Well, this is 3 over 32 minus 4 over 32. So this is negative 1 over 32. Now, the important piece of this is that this is a negative number, which shows that g is actually decreasing at x equals 1, which means that it is not increasing for the whole time between x equals 0 and 4. So we've shown what they asked us to, and we're done with this part of the problem. This last part of the problem is definitely the final boss battle of this one. H of x, they're saying, is x to the n over k, and k is a non-zero constant, n is positive. We want values of k and n so that h meets requirement 2. All right, so let's start by trying to meet requirement 2 again, and then after we get that, they want us to also show h meets these other requirements. But let's start with 2. So they're saying that, again, at x equals 4, the value of the function has to be 1. So that means h of 4 is what we need to figure out. So h of 4, that would be 4 to the n over k. And they're saying that that needs to take on a value of 1. So let's just set that equal to 1. Now, there's not much you can do to solve for n or k at this point because you've got essentially 2 different unknowns. But if we wanted to, we could at least make it less fraction-y and multiply both sides by k to get 4 to the n equals k. Maybe if we do the second part of this condition, we'll get another equation that we can play off of this one to solve a system of equations. But who knows? All right, so the next part of this, the slope of the graph has to be 1. So that means we need to talk about h prime. H prime in general, since n and k are constants, we use our power rule here. That's going to be n over k for the coefficient, and we'll have x to the n minus 1 as the new exponent. We multiply by the exponent, subtract 1 from the exponent if it's a constant. So there's our h prime. Now, we said that this needed to have a value of 1 as well. The slope has to be 1 when we plug in 4. So let's look at h prime of 4. That's going to be n over k times 4 to the n minus 1, and that must equal 1. The slope has to be 1. Well, this is another situation where by itself we can't really do much here. We can multiply both sides by k, again, just on the principle of not liking fractions, I guess. So we can say that n times 4 to the n minus 1 equals k. But we can go a little bit further now, because we've got this equation up here where we have one thing that k equals, and we also see that k equals all this stuff. Playing these off of each other using our substitution method from back in our algebra days, we can say that 4 to the n and 4 to the n minus 1 n have to equal each other if they both equal k. So this gives us an equation we can now solve for n. Now this is a little bit tricky because you've got n in the exponent and in the non-exponent, so that's a little tough. But if you just divide both sides by 4 to the n minus 1, well, you'd just be subtracting the exponents. You would just have 4 to the n minus 1. N's would cancel. You've got plus 1, so you would just have 4 on the left side. Now, if that doesn't work for you, consider what happens if you plug 4 in for n. You would have 4 to the n minus 1 times 4 to the 1. Adding the exponents would give you just 4 to the n. So n does equal 4 any way you want to solve that. We can now actually plug that back in to solve for the k value. So if we do 4 to the 4th, that should give us k. And if you wanted to, you could simplify that to 256. Not necessary, but you could. So let me just rewrite the h function now. That's going to be x to the 4th over 256. And looking ahead at conditions 1 and 3, in condition 1, they're talking about the slope of the graph of h. In condition 3, they're talking about increasing. So to do both of those conditions, I also need to know h prime. So let me go ahead and find that, because I know I'm going to need it down the road. So using my power rule, we've got 4 over 256, which is 1 over 64, and then x cubed. All right, let's satisfy condition 1. So at x equals 0, the value of the function is 0. So basically we're saying h of 0 has to equal 0. h of 0 is 0 to the 4th over 256. That does, in fact, equal 0, so we've met that part of the condition. They also said the slope of the graph is 0. Well, let's plug 0 into h prime and see what happens. H prime of 0 is going to be 0 cubed over 64, also 0. So we've met condition 1. On to condition 3. Between 0 and 4, the function is increasing. To rigorously prove this, we're going to need a little bit of sign analysis, and we also need critical values. So to find critical values, let me just take h prime and set that equal to 0, like so. Now, since we have nothing in the denominator in terms of variables, there's nowhere this is going to be undefined. The only critical values we actually care about are places where h prime does equal 0. And if we set the numerator, x cubed, equal to 0, we see that x must be 0 to make the whole derivative come out to 0. So our only critical value is at 0. The only place h prime can change signs is at 0. That means that everything that's greater than 0, h prime is going to have the same sign. So if we just find a single value of h prime for an x value that's positive, bigger than 0, we've found all the h primes greater than 0. Hey, let's try h prime of 1. H prime of 1 would be 1 over 64. That's a positive number. So that proves then that h is increasing on the interval from really 0 to infinity, but we only needed to show it was increasing on the interval from 0 to 4. So that meets condition 3, and we are done.